Okay, welcome back to another video on the Maths channel. This is your teacher, Mr. Lim here. In this video, we're looking at differentiability and sketching gradient functions from a curve. So by the end of this lesson, you'll be able to determine if a function is differentiable or not, and sketch the general shape of gradient functions from curves. So let's have a look at the first part of this lesson. Is the function differentiable? A function is differentiable at any point where it is continuous and smooth because we can find its gradient at that point. All polynomial functions, such as linear, quadratic, and cubic functions, are differentiable at all points because the graphs are smooth and unbroken. So we can see here, we've got a linear function and it is smooth and unbroken. So we can differentiate this at any point along this curve. If x is minus 8, or x is equal to negative 3.7, or if x is equal to 5.9, we can differentiate it. Same with this one. This quadratic function is smooth and unbroken, so we can differentiate it at all points. Same with this cubic function, smooth and unbroken. However, a function is not differentiable at points where it is discontinuous, so meaning there's a gap or a break in the graph, or when it's not smooth. So in the first two examples, we can see that it is not differentiable here at x equals 0 because it's discontinuous. In the second example, it's not differentiable at this point when x is equal to b because it's discontinuous. And in the last example, it's not differentiable at x equals c because it's not smooth. So not differentiable at x equals 0, not differentiable at x equals b, and not differentiable at x is equal to c. Okay, first two is because they are discontinuous. But for the last one, it's because it's not smooth. So what that means is we can actually differentiate it at all the other points. Okay, if I were to find the gradient of the curve at this point here, the gradient of the tangent, I can work it out. Or at this point, I can work it out. Okay, if I were to work out the gradient of the tangent. However, of all the other, of the ones that I've highlighted, we can't differentiate it at those points. Pause the video, have a go with question A, and see if we can explain why the function below is not differentiable at a, b, and c. Okay, so here are my answers. It's not differentiable at a or b because they are not smooth, and it's not differentiable at c because it's discontinuous. Part B, is the function f of x is equal to x when x is less than 1, or equal to x squared when x is greater than or equal to 1, differentiable at all points? So this is a piecewise function, which means we actually need to graph this to see what it looks like. So I've got when x is equal to 1, anything to the left of that, whenever it's less than x is equal to 1, is going to take this function f of x is equal to x, which means it's going to be a straight line with a gradient of 1. Well, when x is 1, y is equal to 1. Let's make this equal to 1. And it's going to have a gradient of 1. Except this is less than or, this is just when x is less than 1. So we don't use a closed circle here, we use an open circle. Let's complete the second part of this graph to the right of x is equal to 1. So when x is greater than or equal to 1, f of x is going to equal to x squared. So f of 1 is going to be 1 squared, or just 1. That's here. F of 2 is going to equal to 2 squared, which is 4, and etc. We know that this here is a quadratic, is going to give us a parabola, a concave up parabola. So when x is 2, we'll just say this is 4. I know it's not to scale, but it's going to look something like this. So, is the function differentiable at all points? No. Not differentiable at x equals 1 because it's not smooth. It is continuous, but it's not smooth. Okay, let's move on to the second part of this lesson. Sketching the general shape of gradient functions from curves. Here are some helpful tips. When sketching the general shape of the gradient functions, if the gradient is positive, if the gradient is greater than 0, so it's sloping up, then that part of the gradient function is above the x-axis. If the gradient is negative, which means it's sloping down for that part of the function, then for that part of the gradient function, it's going to be below the x-axis. I'll go through a number of these examples for you. And if the gradient of the tangent is 0, then it's just going to be 0 on the gradient function. It's going to be on the x-axis. It's going to be an x-intercept. Now, I like to actually, when I graph this, I always like to graph it underneath the function, and I like to find all the ones where the gradients are 0 first, because I need to know my x-intercepts, and then I'll just go above or below according to the gradients. So let's have a look at the first example. We've got f of x over here, and we want to graph f dash of x. We want to graph the gradient function from this curve. So what I would do is I would graph it, like I said. I like to do it underneath. I like to do it underneath. Now, in this case, the gradient is going to be constant. There's no horizontal gradient. The gradient is constant. If we were to work this out, if I were to just graph maybe a right angle triangle here, it's got a rise of 1, 2, and a run of 1. So the gradient is 2, right? Sloping up, 2 over 1, 2. And the gradient is actually the same for all values of x. The gradient is 2. So I'm just going to draw a horizontal line here at y equals 2. So that means if x is minus 3, the gradient is 2. If x is minus 2, the gradient is 2. If x is 0, the gradient is 2. If x is 5, the gradient is 2. Okay, and we can see that because this is constant. Okay, let's have a look at the second example, B. Here we have f dash of x, and we want to graph the gradient function f dash of x. The first thing I would do is I would write down plus and minus signs or a 0 wherever to describe the gradients for this curve. So if I were to draw the tangents along, like at this point here, the tangent is sloping down, so it's negative. In fact, it's always sloping down, right? It's always sloping down until we get to here. At this point, when x is 0, the gradient is 0 because the line is horizontal. Then at all of these points, the gradient of the tangent is sloping up. It's positive. So instead of doing all that, I'm just using that to explain it to you. I'm going to say that it's sloping down Okay, all sloping down here until we hit when x is 0, then the gradient of the tangent is 0. And then to the right of x equals 0, it's sloping up. Okay, it's all positive. So if I were to graph my gradient function here, okay, just put it underneath. First thing I'm going to do is I'm going to start with when it's 0. When is it 0? When x is 0. So that means I know that my gradient function is going to go through here. My x-intercept is when x is 0. This part tells me that to the left of x equals 0, the gradient function will be below the x-axis. Below the x-axis. This part here, because they're all pluses, tells me that to the right of x equals 0, for my gradient function, it's going to be above the x-axis. And that's it. Let's have a look at question C. We've got f dash of x, we've got f of x for this, and we want to graph f dash of x. We want to graph the gradient function of this curve. So I'm going to say, oh, this is sloping up. Okay, it's got positive gradients until it reaches here. When x is 0, the gradient is 0. And then for this one here, it's still sloping up, right? So I'm going to draw my plus signs. Alright, so if I were to graph my gradient function now, let's put it underneath there. I'm going to start with this. At what x value is the gradient equal to 0? At 0. Oops. This part here tells me to the left of x equals 0, the gradient function is going to be above the x-axis. And this part here, to the right of x equals 0, tells me that my gradient function will be also above the x-axis. And I'm done. Now you might notice a pattern here. Like for part B and part C. Part B is f of x. Let's just say that's x squared minus 3. When we work out the gradient function of that, when we differentiate this, we get 2x. Right, f dash of x is equal to 2x, which is a straight line. And here's our straight line. Here we've got f of x, let's just say that's x cubed plus 1. If we were to differentiate this, we get 3x squared, right? It's like saying 3x squared. Well, x squared, this tells us it's a concave up parabola, and that's exactly what we have. Now, the trick here is to realize that when we have a look at what kind of graph the function is, because this one's a cubic, the gradient function will be 1 less than that. It'll be x squared, something x squared, right? That's going to be the highest power, which means it's going to be a parabola. Here, the function is x squared. The gradient function is going to be 1 less than that. It's going to be 2x. Well, it's just going to be x in this case. So it's like, it's a straight line, which is what we have here. So that's the trick. It helps you know pretty much how many turning points there are. Because it's x squared, there's only one turning point in our gradient function. Alright, D. F of x is equal to this function here. Now I don't have any values, but I'm just gonna graph, I'm gonna just write all my gradients sloping up, and then at this point it's 0. This point is still sloping up, then it's 0 again, and then all of these is sloping down. Okay, so if I were to graph my gradient function, we've got f dash of x. Where is it 0? When x is 0, and when x is whatever this is. We can call it x1. Now, when I graph this, x is 0, and I'm just going to like come down all the way here. Right there. That's my other x-intercept. Now, to the left of x equals 0, it's positive, so it's above the x-axis. To the right of 0, but to the left of, let's just call this x1, is also positive. So that means it's above the x-axis. This part here, that tells us it's below the x-axis. So it's going to come down. To the right of x1, it's going to be below the x-axis. So how do we finish this off? Well, I'm just going to make it come back down, and that's it. Let me go through one more example with you, and I'll show you my shortcut, and then you can have a go with question F. So for question E, we've got f of x here, and we want to graph f dash of x, the gradient function. So I'm going to write, okay, that's stepping up, 0, sloping down, 0, up, 0, down, 0, and then up. Okay, so I'm going to draw my axes. Okay, draw my axes. Where is it 0? At this point, this one, and this one. So, at this point, right there, it's going to be an x-intercept. At this point, it's going to be an x-intercept. At this point, it's going to be an x-intercept. And at this point, it's going to be an x-intercept. The next thing I would do is actually I would look at the left-hand side and the right-hand side only. The left-hand side says it's above the x-axis, so I'm just going to go up. The right-hand side says it's above the x-axis, so I'm going to go up. And then I'm just going to fill in the rest. So this one says down, and then it's above, and then it's below, and that's it. This is the general curve of the gradient function. Now, really, it could be all the way down here and then come up. Okay, it could be something like that, but that's the general shape of the function, and that's all we need to learn for now. Okay, pause the video, have a go with question F. Okay, so what I've done was I've labeled the gradients along the function. I've put in all my x-intercepts accordingly. And now I'm going to do my left side, which is below. I'm going to do my right side, which is above. And then I'm going to fill in the rest. So from the left to right, this bit's above, then it's below, then it's above, and then it's below. And that's the general shape of the gradient function of that curve. Okay. Pause the video, see if you can have a go with G, H, and I. Okay, in question G, I've labeled my gradients. So I'm going to just record where the x-intercepts are. Right here. Those are my x-intercepts. I'll do the left part and the right part. We've got negative, we've got below, we've got above. Sorry, let me use red. Between these 2 points, it's above. Between these 2 points, these 2 x values, it's below. And that's it. That's the general shape of the curve. Now, for H and I, you might be thinking, oh, it's always positive. There's nowhere along both of those curves where the gradient is 0, and that's correct. Which means when we graph f dash of x, so here's f of x, if I were to graph f dash of x, is always going to be above the x-axis. Now, if we were to think about how the steepness of these curves, this one's quite flat, right? Over here is quite flat, then it gets steeper, and it gets even steeper. So when we graph our gradient function, we need to keep that in mind. It's always going to be above the x-axis because it's always positive. Now, let's say to the left of x equals 0, it's really, really flat, which means the gradient is very close to 0. It's very close to 0. So to the left of x equals 0, very close to 0. Then it's getting steeper at this point. At this point, it's getting steeper. So the gradient is going to be more than 0. Let's just say it's here. At this point here, it's even steeper. So that means it's going to be even further away from 0. So now, that should be enough for us to realize we have enough to graph the gradient function of this curve. And it actually looks exactly the same. This is a special function called an exponential function. We will learn about this later, but basically, when f of x is equal to e to the x, and we were to differentiate that, f dash of x also equals e to the power of x. They look exactly the same. Okay, part I, we've got f of x here, and you'll notice, hey, exactly the same as h. It's always sloping up, never sloping down. There's nowhere where the gradient is horizontal. So how are we going to graph this one? Is it going to be the same as h? Well, again, we need to think about the steepness of these gradients. So over here, right, at this point, it's really steep. Over here, the tangent is definitely not as steep. Over here, it's even flatter. In fact, as x approaches infinity, it looks like it's getting closer and closer to a horizontal gradient of 0. So what we're going to do is, because all of these are plus signs, the whole thing has to be above the x-axis when we graph our gradient function. But to the left of x equals 0, it's really steep, which means that the gradient is going to be really, really high. Really high. As x approaches infinity, we can see it's getting flatter and flatter, which means it's getting closer and closer towards 0. So we can see here, it's getting closer and closer towards 0 as x approaches infinity. And that's the general shape of that curve for the gradient function of this curve up here. Okay? Alright, that's it for this video. So now you know where a function is differentiable or not, and how to sketch the general shape of gradient functions. We don't really need to know what these turning points are yet. You will learn that in year 12, how to actually work that out. Thanks.